Hello students, so here we are with the lecture 7 of Haloalkanes and Haloarenes class 12. So let's see the nucleophilic substitution reaction. This we have already done in the last lecture, it's just a revision. So with aqueous NaOH or aqueous KOH, when the alkyl halide is boiled with aqueous KOH or aqueous NaOH, then what is formed? Alcohol is formed. So alkyl halide plus aqueous KOH gives you alcohol plus KX. So instead of RX, if we take methyl chloride and react it with aqueous KOH, you get methyl alcohol and potassium chloride. Okay, so when you react alkyl halide with NaOH, you get alcohol plus NaX. That means methyl chloride when reacted with NaOH gives you methyl alcohol and NaCl. So basically, which is the nucleophile here? OH minus. So this OH minus nucleophile is replacing the halide nucleophile. So halide nucleophile being weaker, it leaves the position and forms a leaving group, and OH minus takes its place, right? Then with moist silver oxide. Now moist silver oxide is what? Silver oxide to which water is added. When you add water to silver oxide, then it forms silver hydroxide. So when alkyl halides are reacted with moist silver oxide and heated, boiled with moist silver oxide, you get what? Alcohol plus silver halide. So instead of RX, if you take methyl chloride or chloromethane and react it with moist silver oxide, you get methyl alcohol and AgCl, right? Then with KCN. So KCN, when alkyl halide is boiled with alcoholic solution of potassium cyanide, it forms alkyl cyanide. Here, so alkyl halide plus KCN forms alkyl cyanide plus KX. So what is the nucleophile here? Cn minus. So X minus forms a leaving group and Cn minus takes its position and RCN is formed. Yeah. So when you take methyl chloride and react it with alcoholic KCN, you get methyl cyanide plus potassium chloride. The IUPAC name of methyl cyanide is what? Ethane nitride. So chloromethane forms ethane nitride, right? Then with AgCN, when alkyl halide is reacted with silver cyanide, it forms alkyl isocyanide. So alkyl halide plus AgCN, it forms alkyl isocyanide plus silver halide. So instead of alkyl halide, if we take an example of methyl chloride reacted with AgCN silver cyanide, you get methyl isocyanide plus AgCl. Here also you have to heat. Now this Cn is an ambident nucleophile. The ambident nucleophile means the product can be formed with C or with N. So when you react it with KCN, KCN is an ionic compound and thus the product formed is alkyl cyanide because electronegativity of nitrogen is more. So Cn, this carries a negative charge and the alkyl links through C. So it forms alkyl cyanide. But AgCN forms a covalent bonds with C. So N is available for bonding. So when you react alkyl halide with AgCN, it is forming alkyl isocyanide. So Cn is an ambident nucleophile. It can form product through by N or by C. When it forms a product through C, it forms cyanide, and when it forms a product through N, it forms isocyanide. Clear? So reaction with ammonia now. When alkyl halide is boiled with excess of alcoholic solution of ammonia under pressure, it forms amines. So alkyl halide plus ammonia under pressure, heat under pressure gives you alkyl amine plus HX. Okay. So here what is the nucleophile? NH2 minus is the nucleophile. So instead of alkyl halide generally, this is called the general reaction. The reactions with R is called the general reaction. So here instead of RX, if I take methyl chloride plus ammonia, alcoholic under pressure, heated, you get methanamine plus HCl. The position of chlorine is taken by NH2. So here the nucleophile is what? NH2 minus, and that takes the position of chlorine. Chloride ion forms the leaving group. Yeah. Then reaction with OR. Then when alkyl halide is boiled with sodium alkoxide, it forms ethers. This reaction is also known as Williamson synthesis. So when alkyl halide is reacted with sodium alkoxide, it forms ether, dialkyl ether plus sodium halide. Okay, so instead of Rx, if I take methyl chloride and I react it with sodium ethoxide, it forms methoxyethane plus NaCl. Okay, how is this sodium alkoxide prepared? So sodium alkoxide is basically prepared by reacting alcohol with sodium. When you react alcohol with sodium, you get sodium alkoxide plus hydrogen gases evolved. Here, so this reaction of formation of ether from alkyl halide and sodium alkoxide is called Williamson synthesis. Clear? What is the nucleophile here? OR minus. Alkoxide ion is the nucleophile here. Okay. Then formation of esters. When alkyl halide is reacted with silver salt of carboxylic acid, you get ester plus silver halide. Clear? So instead of alkyl halide, if I take methyl chloride and react it with silver propanoate, you get methyl propanoate plus silver chloride. So basically silver chloride is formed and this is propanoate and that reacts with methyl and forms methyl propanoate, which is an ester. Clear? Then with KNO2, potassium nitride. When alkyl halide is treated with potassium nitride, it forms alkyl nitride. Okay. So alkyl halide plus KNO2 gives you RONO and potassium halide. So here again, potassium, this NO2 is a ambident nucleophile. It can form product through O or it can form product through N. So when it is reacted with ionic compound KNO2, it forms product with a more electronegative atom, that is RONO, that is alkyl nitrite. Okay, so methyl chloride when reacted with KNO2, it forms methyl nitrite plus KCl. While if it is reacting with silver nitride, then it forms nitroalkane. So silver alkyl halide plus silver nitride gives you RNO2 plus silver halide. So methyl chloride plus silver nitride gives you nitromethane plus silver chloride. Clear? So in all the above reaction where boiling is written, the symbol delta has to be used above arrow for heating or boiling. Clear? So when alkyl halide is reacted with KNO2, what is the product form? Alkyl nitride. That means this alkyl is bonding through O. But when it is forming a covalent bond, silver with nitrogen is forming a covalent bond, then here this links through N and alkyl nitroalkane is formed along with silver halide. Clear? So when covalent compound is there, then it is forming nitroalkane. But when ionic compound is there, then this links with the more electronegative atom, R links with the more electronegative atom and it forms alkyl nitride. Clear? So in short, now just summarize. I've summarized all the reactions here. So this alkyl halide, when reacted with aqueous KOH heated, what do you get? ROH plus KX. When it is reacted with moist silver oxide, you get ROH plus AgX. What is ROH? Alcohol. So alkyl halide forms alcohol when it reacted with aqueous KOH, aqueous NaOH, moist silver oxide. Okay. Then alkyl halide when reacted with alcoholic KCN and heated, you get alkyl cyanide. But when it reacts with alcoholic AgCN, it forms alkyl isocyanide. Clear? Then alkyl halide when reacted with ammonia, it forms amine. When reacted with sodium alkoxide, heated, forms ether. This reaction is called Williamson synthesis. Then when reacted with silver salt of carboxylic acid, then you get ester plus silver halide. When reacted with KNO2, it forms alkyl nitride. But when reacted with silver nitride, it forms nitroalkane. So this NO2 is also ambident nucleophile and CN is also ambident nucleophile. So I hope the nucleophilic substitution reactions, all the nucleophilic substitution reactions in our syllabus are summarized here and are clear. Okay. Now let us see the mechanism of the nucleophilic substitution reaction. So in the first slide of the last lecture, I told you that how the pattern is that when alkyl halide is reacted with the nucleophile takes the position of the halogen, halide ion, and halide ion forms a leaving group and nucleophile takes its position. So why there is polarity on the alkyl halide, that also was told to you, but I'll just tell again that in the halogen and this carbon halogen bond is polar, because this halogen is having a high electronegativity. It pulls the electrons towards itself and it forms delta negative charge. Carbon gets a delta positive charge and it gets polar. So then halide ion is replaced by the nucleophile. So stronger nucleophile takes the position of weaker nucleophile and does the substitution reaction. So the substrate here is what? Substrate is this alkyl halide. So basically the substrate is undergoing two changes. First is the breaking of CX bond and the formation of new bond with nucleophile. Okay, so basically two things are happening. One, the CX bond is getting broken and another, the CNU bond is being formed. Clear? So this mechanism of SN reaction goes either in one step or in two steps. So based on that, it is categorized, it is observed in Sn1 reaction mechanism and Sn2 reaction mechanism. So basically it's of two types, Sn1 mechanism and the Sn2 mechanism. So let's see first the Sn2 reaction mechanism. So methyl bromide when reacted with aqueous KOH gives you methyl alcohol plus potassium bromide. Now if you find the ionic form of the reaction, it is methyl bromide plus OH minus ion. OH is what? A nucleophile, stronger nucleophile, and it takes the position of Br. Br forms a leaving group and methyl alcohol is formed. Yeah. Now if you write the kinetic expression of this reaction, this you have studied in the chapter of chemical kinetics, how to write the expression, that is rate is directly proportional to the concentration of the reactant. So here rate is equal to K into CH3Br concentration and the OH concentration. So here rate depends on both substrate and nucleophile. Which is the substrate here? Methyl bromide. And which is a nucleophile? OH minus. So basically the rate is dependent on both substrate and nucleophile. Therefore, this reaction is called the bimolecular reaction because the rate is dependent on two concentrations, concentration of the substrate, that is methyl bromide, and concentration of the OH minus, that is the nucleophile. So the rate is dependent on both the molecules, therefore it is a bimolecular reaction. Clear? And how do you calculate the order? Order is the power to which the concentration terms are raised. So here methyl bromide, what is the power? 1, and OH minus, what is the power? Also 1 in the kinetic expression. So order will be what? 1 plus 1, that is equal to 2. So here the molecularity is also 2 and the order is also 2. Therefore we call the reaction as Sn2 reaction. Okay, S stands for substitution, N stands for nucleophilic, and 2 stands for bimolecular. So it is basically the bimolecular substitution reaction. So here the rate of the reaction depends on concentration of both reacted molecules, that is substrate and the nucleophile. Therefore it is called what? Substitution nucleophilic bimolecular reaction. Correct? So here rate of chemical reaction is influenced. Always you remember rate is dependent on the slowest step. So this was the slowest step, the formation of methyl alcohol from methyl bromide and OH. I'll just show you the how the reaction mechanism happens. So but just for the information you should know that rate of a chemical reaction is influenced by the chemical species taking part in the slowest step of its mechanism. Okay, so in the above reaction only 2 reactants are present and the rate is influenced by both the reactions. Both the reactants influence the rate of reaction. So basically it is a single step reaction. Okay, let's see now. Here this is methyl bromide. Okay, methyl bromide, you see this is the carbon to which 3 hydrogens are attached. See, this hydrogen is in the plane and bromine is in the plane. This CH is below the plane and this H which shown with the wedge line is above the plane. This is towards you, this is inside. So when the OH attacks methyl bromide, okay, so what happens basically? The molecule gets reordered, redisturbed, restructured. So here you see the 3 H bonds, they shift in the trigonal form and the OH is starts forming bond with carbon and bromine starts leaving. Okay, so a transition state is formed. Okay, which is a temporary state And here you see OH carries minus half charge and Br carries minus half charge. So the negative charge of the nucleophile gets distributed between OH and Br. So carbon OH bond is about to form and carbon Br bond is about to break. So this is the leaving group and this is the coming group. Okay. So here you see what happens on next. Next, this OH gets attached. This bond becomes uh, this bond is formed and the Br bond breaks and Br negative is formed. Clear? So here you see this in this CH3Br, bromine was on the right hand side, but here you see OH is on the left hand side. So what has happened in this? Basically, the inversion of configuration has happened. It has got inverted. Okay. So this reaction happens in one single step. First transition state is formed and then the product is formed. So product is having what? Inversion of configuration. So basically in this step, first is the formation of transition state, and then second is the inversion of the configuration. So what happens, basically the backside attack takes place. OH attacks carbon from the backside. This transition state is formed. Here carbon is bonded to OH and Br both, and the product is formed with the inverted configuration. Okay, clear? Basically, the reaction is happening in one single step. So bond breaking and bond formation takes place simultaneously. Okay, now this reaction, any reaction, you require a solvent. The solvent required here is what? Polar aprotic solvent. That means a protic solvent means with a solvent that doesn't contain proton. So if you see CH3, CO, CH3. So there is a polarity between C and O, carbonyl group. So there is a delta positive charge on carbon and delta negative charge on oxygen. So there is a polarity in this CO bond, but there is no H plus present. So it does not give proton. So basically the polarity is developed because of this carbonyl group. So this solvent is known as polar aprotic solvent. So basically polar or aprotic solvent is required for the reaction. Okay. Now if our substrate will be optically active, that means to the carbon 4 different groups will be attached. So here in this example you saw CH3Br, but instead of CH3Br, if you have H attached to carbon, then CH3, then C2H5 and then Br. So if the carbon is optically active, that means 4 different groups are attached to the carbon, then the product form will be having what? Product form will be inverted product. So if the reactant is levorotatory, the product will be dextrorotatory. Or if the reactant is dextrorotatory, the product will be levorotatory. Clear? So if optically active substrate, inversion product will be formed. So if our optically active substrate is there, okay, then product form will be what? Optically active only, but then it will be inverted. So if the reactant is or the substrate is dextrorotatory, the product form will be levorotatory. If the substrate is levorotatory, the product form will be dextrorotatory. Clear? Then rate of reaction is inversely proportional to the steric hindrance. What do we mean by steric hindrance? The cloudiness of the group attached. So backside attack not possible if cloudiness is more. How soothing will be the backside attack? Backside attack will be the most soothing if the groups attached are less clouded. So if H is attached, then it will be more suitable. So the reactivity order will be what? Methyl, then ethyl, then dimethyl, that is isopropyl, then tertiary butyl. So the most reactive will be which one? Methyl bromide, then ethyl bromide, then isopropyl bromide, then tertiary butyl bromide. That means the reactivity will be this. This is what? CH3 is what? 0 degree. This is 1 degree carbon. This is containing 2 degree carbon and this is containing 3 degree carbon. That means the most reactive will be the 0 degree carbon containing halide. Okay, because there the cloudiness will be less, because rate of reaction is inversely proportional to the steric hindrance or the cloudiness of the group. So more groups attached, lesser will be the rate of reaction. So this Sn2 mechanism will be more feasible with methyl bromide, then ethyl bromide, then isopropyl bromide, which is a 2-degree carbon, and then the tertiary butyl bromide, which contains the 3-degree carbon. Okay. Now, if you see this nucleophile, rate of reaction is directly proportional to the leaving group. So, more easily the leaving group leaves, more will be the rate of reaction. So, more the bond length, more easily the bond will break. Yeah. So, the maximum bond length is in Ri, then RBr, then RCl. So, Ri will be have the maximum rate of reaction, then RBr, and then RCl. Because more the bond length, Ri will be having more bond length than RBr, then RCl. Okay. So, more bond length, more easily the bond breaks, and more easily the group will leave. Clear? So basically the rate of reaction depends on what? Firstly on the steric hindrance. It is inversely proportional to the steric hindrance, and rate of reaction is directly proportional to the leaving group. Clear? So now again let us see what happened in the mechanism. First there is a firstly the reaction is taking place in one single step. So bond breaking, bond forming, all are happening simultaneously. Clear? Then backside attack of the nucleophile. So nucleophile attacks from the backside. Why it attacks from the backside? No, why not from the front side? Because when it comes, this is a Br is a negative group. OH is also a negative group. So if it comes from the same side, what will happen? There will be repulsion. So that is the reason it is attacking from the backside. Clear? So nucleophilic attacks from the backside to avoid the steric hindrance and electrostatic repulsion between the incoming nucleophile and the leaving group. Clear? Then what happens in the transition state? The nucleophile and the leaving group are bonded to the carbon, and there is a partial bonds and there is a partial negative charge gets distributed on both the nucleophiles, which is going to form the bond and which is going to leave. Okay, and then what happens? Then the product is formed, the COH bond is formed, and the Br minus leaves, and there is inversion of configuration. So the transition state contains which carbon? Penta-coordinate carbon, where it is forming 3 sigma bonds in one plane, making 120-degree angle, and 2 partial covalent bonds along a line perpendicular to this plane. Clear? So if someone asks, this question is asked that what is the valency of the carbon here? It is penta-coordinated carbon. So it forms 3 sigma bond, and the bond angle is what? 120-degree in the same plane, and 2 partial covalent bonds that are perpendicular to the plane. Clear? Then I told you about the inversion of configuration. Inversion of configuration is just like the inverted umbrella. If there is wind, sometimes the umbrella gets inverted. So basically in Sn2 mechanism of an optically active substrate, the product is found to have opposite configuration, or also known as Walden inversion, which is result of the backside attack of the nucleophile. So there is 100% inversion of configuration. Okay, so that is we saw just now. So if you take the optically active reactant, then you get an optically active product, but the product is inverted. That means it shows opposite rotation. So if the reactant is levorotatory, the product form will be dextrorotatory. If the reactant is dextrorotatory, then product form will be the levorotatory. Okay, so this inversion of configuration analogy is like inversion of the umbrella in the wind. Clear? Okay, thank you. Okay. Then one more thing, energy profile diagram. Now what is energy profile diagram? Energy profile diagram is a diagram of the potential energy against the reaction coordinates. So as the reaction progresses, how the energy changes takes place. So this energy profile diagram is basically telling you that. So here you see the reactants were what? Methyl bromide reacted with the OH nucleophile. So reactants were methyl bromide and OH. Let's say the energy or potential energy of their reactants is here. So when the methyl bromide, the OH nucleophile approached methyl bromide from the backside, then what happened? The transition state was formed where OH was about to form bond and Br is about to Br bond is about to break, and at that instant transition state is formed. So you get a penta-coordinate carbon to which 3 H's are attached, and OH nucleophile is about to form bond and Br nucleophile is about to break. Br bond is about to break. Okay, so at that point the energy of the system is more, and this difference in energy between the reactants and the transition state is called activation energy. So this delta E you see is the activation energy. So this energy profile diagram, you see how the reactant energy increases, and then gradually when the product is formed, the energy drops down and methyl alcohol and bromide ion is formed. So this energy difference between the energy of reactants and energy of the product is called the heat of the reaction. This heat of the reaction of the products is less than the reactants. Therefore, it is a exothermic reaction. Okay. So you see the bell-shaped diagram here between the potential energy and the reaction coordinates. The reactants, when the reactant energy, this is the point of the reactant's energy. The energy increases as the OH is about to form, the transition state approaches. Then when the formed transition state, when the product is formed, then energy decreases. Okay. So what is delta E? Delta E is the activation energy, that is the difference in energy of the transition state and the reactants. Clear? Okay, thank you.